So hello everyone, I am Lynn Clark and I make code cartoons. And I also work at Mozilla. So as you heard, I'm in the Emerging Technologies group. And so that's things like the Rust programming language and WebAssembly, which is a really fast way to run programming languages that aren't JavaScript in the browser or in something like Node. And we also work on Servo, which is a new web engine. And I'll be talking about all of those things today because they're all a part of the future of the browser. So why talk about the future of the browser? Because browsers are facing a challenge, and whether or not browsers meet this challenge could change the web as we know it. What is the challenge? Browsers need to get faster. Content on the web has changed since the early days. In the early days, speed really didn't matter that much. We were just looking at static documents. So as soon as that document was downloaded and rendered to the screen, the browser was pretty much done with its work. It might need to do a little bit of work when the user scrolled or something like that, but there was nothing too complicated. Then people started pushing the boundaries. They started thinking, what can we do with this web besides serving static documents? And so pages started getting interactive and they started having animations. For example, do you remember when everybody went wild for drop-downs? And you had everybody creating these fancy slide-down menus with jQuery? Once that was a part of the page, the web page wasn't just being painted to the screen once. With every change, it needed to be repainted. And when you had these animations, the screen needed to be repainted multiple times for each change. So for each change, there were multiple repaints. And if you wanted the interactions to look smooth, if you wanted those animations to look smooth, those repaints needed to be happening at a certain rate. They needed to be happening 60 times per second. So that meant that you only had 16 milliseconds to get all of the work done. So browsers made all sorts of changes to come up to speed and to accommodate these new ways, these new applications that were on the web and get up to 60 frames per second. But as is the way with the web, content authors started pushing the boundaries even more. They started not just making their web applications more interactive, but bringing whole new classes of applications to the web. So things like PC games, and companies started talking about bringing things like Photoshop to the web. These new classes of application are taxing the web even further and making it clear that things like JavaScript need to get even faster. It's not just content authors that are pushing these boundaries either. It's also the hardware vendors. So for example, the new iPad is going from 60 frames per second to 120 frames per second. That means that the browser has half as much time to do just as much work. And new kinds of content are coming to the web and pushing this even more. So for example, with VR, you have two displays, one for each eye, and each of those has to be going at least 90 frames per second to avoid motion sickness. And each of those displays can be up to 4K resolution, which means that you have lost more pixels in each of those displays. So let's think about what that change means. If you're running a website on a 13-inch MacBook Pro, you have about 16 milliseconds to fill in between 4 and 4.5 million pixels. With the next iPad, you have half as much time, 8 milliseconds, to fill in 3 million pixels. And with a VR experience, you have 11 milliseconds to fill in up to 16.5 million pixels. And that doesn't even include any heavier JavaScript needs that that application might have. So that is a huge leap that browsers need to make in order to keep up. What happens if the browsers don't keep up? Well, as more and more people buy these new devices and as more and more content moves into these heavier applications, if browsers don't keep up, people are going to stop seeing the web as the default place to put their content. And this could mean that the web as we know it withers. And that's a pretty scary thought. But to be honest, I'm not too worried. I'm confident that browsers can make this leap. And the reason that I'm confident is that at Mozilla, we've been working on this problem for the last 10 years. We've been looking at the direction that computer hardware is going, and we've been figuring out the new way that we need to program the browser to keep up with those changes. And the answer is parallelism. The future of the browser is parallel. We've only started taking advantage of this in Firefox, but we're already seeing some really big wins from it. And every indication is that this new way of doing things can get the browser where it needs to be. So in this talk, I want to explain what browsers need to change in order to make this leap. But before I do that, let's talk a little bit about what the browser actually does. So I'm going to start with the rendering engine. And that's the part that does the most important thing in a browser, which is take the HTML and CSS files and turn that into pixels on the screen. And it does this in 5 steps. But to make it simpler, I can split that up into 2 different groups. So the first group takes the HTML and CSS, and it figures out a plan. It figures out what the page should look like. It's kind of like a blueprint, specifying where everything goes on the screen. So it specifies things like the widths and the heights and the colors of all of the different things on the screen. The second group takes this plan and turns it into the pixels that you see. So now let's look more closely at each step in this process. The first step is parsing. And so what the parser does is turn the HTML into something that the browser can understand. Because when the HTML comes in, it's basically one big long string of text. It's like a paper ribbon that has all of these characters on it. And so the parser is just going to go along with a pair of scissors along that paper ribbon and cut out the different elements and put them into a family tree of the page. So when it sees the opening tag for a div, it will cut that out and put that up in the family tree. And then when it gets to the next element, it will cut that up, say that's a paragraph, a p tag. It will cut that out, put that underneath, and connect them with that parent-child relationship. So this family tree is called the DOM tree, the Document Object Model. And it's called that because it provides a model of the document, which we can use to make any changes that we want to the document and the way it shows up on the screen. Like if JavaScript wants to get rid of some of those paragraphs, all it has to do is take them out of that family tree, and then they'll disappear from the screen. So at the end of parsing, we have this family tree, the DOM tree. And that tells us about the structure of the page and the parent-child relationships. But what it doesn't tell us is what any of those should look like. In order to figure out what they should look like, we need to take the CSS that we've downloaded and figure out which styles apply to which elements in this tree. So that's the next step, CSS style computation. I think of CSS style computation like a person filling in a form for each one of these elements in the tree. The form is going to say exactly what that element looks like. And it has more than 200 form fields for doing that. There's a form field for every single CSS property. And this form needs to be completely filled out. For every single element, you need to have a completely filled out form. So at the end of CSS style computation, you have all of those filled out forms. But there's still a little bit more that we need to do. We need to figure out how wide and how high things are going to be and where they'll be on the page. So the next step, layout, is what takes care of this. It looks at the dimensions of the browser window, and from that, it calculates all of the relative values. So if a div is 50% of its parent, it will figure out what that means. It will also do things like break up a paragraph element into multiple elements, one for each line in the paragraph. And this is how it knows how many lines high it needs to make that containing box. The output of this step is another tree. In Firefox, we call it the frame tree. But in Chrome, it's the render tree, and Edge, it's the box tree. All of them are basically the same thing. It's the ultimate plan for what this page should look like. Now we move on to the next part of rendering, which is turning that plan into the pixels on the screen. Filling in pixels can take a long time, especially when there are a lot of things rapidly changing on a page. And because of this, browsers have tried to find ways to reduce the work and make it faster. One way that they've done this is by splitting up what gets shown into multiple different layers. So these are layers kind of like you would have in Photoshop, or I think of them like the layers that you would have in an old-time animation, like in Bugs Bunny cartoons. You have the background on one layer and the characters on another layer. Then if the characters move, you don't need to repaint the background. The background layer can just stay the same, only the top layer needs to change. So the first step in this process is called painting. That's where we create these layers. And the next step is called compositing. That's where you take these layers and you put them together and then basically just take a picture of that and put it on the screen. And that's how the page gets rendered. Now I framed this as the way that a web page's content goes from HTML and CSS to pixels. But what you might not know is that there's actually another part of the browser, the tabs, the URL bar, all of that stuff. And that part's actually separate. It's called the browser Chrome. In some browsers, such as Firefox, rendering browser Chrome actually is handled by the rendering engine. So you have this rendering engine, and it has two different tasks. It has to render the inside of this window, which is the content, and the outside, which is the Chrome. And actually, it's not just two tasks, because for any tab that you have open, there's going to be a new content window. Even if its pixels aren't showing because it's not the selected tab, it could be running JavaScript. So the browser has multiple things to do, and they're all pretty independent of each other. And this is one of the earliest places where parallelism was introduced to the browser. In 2008, you started seeing a browser take advantage of new hardware to run these tasks at the same time independently. But it wasn't us that did that. It was Chrome. When Chrome launched, its architecture was already using parallelism like this. It's called the multi-process architecture, and it's one of the reasons why Chrome was faster and more responsive than Firefox when it was first released. Now, I feel like I should take a step back here and explain what this all really means, what hardware change specifically Chrome was taking advantage of, and what that change made possible. And this may be something that a lot of the folks in this audience already know, but I'm just going to do a little crash course in computers and how they work so that everybody's on the same page. So a little computer architecture crash course. You can think of a computer like you think of a brain. There are different parts of this brain. There's the part that does the thinking. There's the part that has short-term memory. And these two are pretty close together in the same part of the brain, the CPU. Then there's the long-term memory. And so all of these different parts have names. The part that does the thinking, that's the arithmetic and logic unit. The short-term memory, those are called registers, and those are on the CPU. And the long-term memory is called random access memory, or RAM. Now, in order to get this brain to do anything, we have to give it an instruction. And this instruction is going to tell us what we need to do with some bit of the short-term memory. So each box of short-term memory is going to have a label so that we can actually put that in the instruction, so we can tell the computer what part of the short-term memory we need to work with. So for example, we could add a number to a value that's in short-term memory to get the result. We could add 1 to the value that's in R4. Now, one thing you might have figured out from this is that we can only do one thing at a time. This brain can really only think one thing at a time. And that was really true of most computers, from the earliest computers until the mid-2000s. But even though these computers had this limitation for so long, they were still getting faster. Every 18 months or 2 years, they were getting twice as fast. You could run twice as many instructions on them in the same amount of time. What made it possible for these computers to get faster was something called Moore's Law. The little electrical circuits that you use to make up the different parts of the CPU were getting smaller and smaller, which meant that more and more of them could fit on a single chip. So with more of these building blocks, you can make more powerful components. And also, there was less distance for the electricity to travel between them. So they were able to work together faster. But of course, you can only make things so small, and there's only so much electricity that you can course through a circuit before it starts burning up. In the early 2000s, these limitations were becoming apparent. Chip manufacturers had to think, how are they going to keep making faster and faster chips? The answer that they came up with was splitting up the chip into more than one brain, basically making it possible to think more than one thought at a time in parallel. These separate brains that the CPU has are called cores. When you hear people talk about a multi-core architecture, this is what they're talking about. Even though each one of these cores or brains is limited in how fast it can think, if you add more of them, they can do more in the same amount of time. But the thing is, in order to take advantage of this, you need to be able to split up the work that you have across these different cores. Unlike before, where the speedups were happening automatically without programmers having to do anything, these speedups actually require programmers to change the way that they code. And this is actually harder to do than you might think. So imagine that two of these cores need to work on the same bit of long-term memory. They both need to add something to it. Well, what number is going to end up in long-term memory at the end of it? Who knows? It depends on the timing of when different instructions run on the different cores. So let's walk through an example of this. We'll start with the number 8 in long-term memory. Both cores need to add 1 to it, so our end result should be 10. Now, instructions have to use data, they have to use things that are in short-term memory. And each core has its own short-term memory. So let's say the first core pulls 8 from long-term memory into its short-term memory. The core adds 1 to get 9, then it replaces the value in long-term memory. So this means that the other core now has access to the result of that calculation. So the long-term memory holds 9 now. Then the second core pulls 9 from long-term memory into short-term memory. It adds 1 to get 10, and then it writes it back to long-term memory. So our end result is 10, and all is good. But it wasn't guaranteed to end up this way. Let's see what happens when these instructions happen in a different order. The first core pulls 8 from long-term memory, and then the second core pulls 8 from long-term memory. And you might already see the problem here. The first core adds 1 to get 9, and then it writes 9 back into long-term memory. Then the second core adds 1 to get 9, and it writes 9 back into long-term memory. So we end up with a result of 9, which is not what we wanted. This kind of bug is called a data race. When you have parallel code with shared memory, so 2 different cores that are working with the same part of long-term memory at the same time, you're very likely to have these data races. One way to get around this is to choose tasks that are pretty independent of each other so that they don't need to share memory. Now, let's go back to the Chrome and the content example that we were looking at before. You might remember I said that these are all pretty independent of each other. That means that they're perfect for this kind of parallelism, where you don't need to share memory between them. And that's called coarse-grained parallelism. That's where you split up your program into some pretty large tasks that can be done independently of each other, but at the same time. It's actually pretty straightforward to do this. You just need to figure out those large independent tasks. So Chrome was doing this from the beginning. The Chrome engineers saw that if they were going to have a fast browser, they were going to need to have some level of parallelism. Around the same time that Chrome was figuring this out, and seeing that if they wanted to have a fast browser, they were going to need to take advantage of this parallelism, we were seeing the same thing. We knew that we were going to have this coarse-grained parallelism in our browser too, if we were going to keep up. And we do now, although it took us a while to get there. It was a multi-year effort. We started testing our multi-process architecture in Firefox 48 with a small test group of users, but it wasn't until this past summer with Firefox 54 that we turned it on for all users. It took us a while to get there because we weren't starting fresh like Chrome was. We had a bit of a bumpier road. We were starting with this existing code base, which was developed before multi-core architectures were prevalent. And we needed to figure out how to break apart this code base without breaking anything for our users while we were doing it. So we needed a plan for that. But we didn't just stop at making plans for adding coarse-grained parallelism to the browser. Because when you have this kind of coarse-grained parallelism, there's a good chance you're still not making the best use of all of your cores, of all of your hardware. For example, you might have one tab that's doing a whole lot of work, but the others might not be doing much at all. That means those other cores are sitting idle. So you're not getting the kind of speed up that you can with a parallel architecture. We saw that if we wanted to make a browser that was really fast, we couldn't just add this coarse-grained parallelism. We had to add fine-grained parallelism too. So what is fine-grained parallelism? That's where you take one of these big tasks and you split it up into smaller tasks. These can be more easily split up across these different brains, across the different cores. But that does usually mean that you're going to have to share memory, as I was talking about before. And this opens you up to those data races. These data races are nearly impossible to avoid when you have shared memory, and they're incredibly tricky to debug. The thinking at the time was basically that to safely program in parallel, you kind of have to have a wizard-level understanding of your language. One of the distinguished engineers at Mozilla actually put a sign about 8 feet high saying, "You must be this tall in order to write multi-threaded code." Now, of course, when you have a project like an open source browser, where you have thousands of engineers at all different skill levels contributing to a code base, you can't code in a way that requires a wizard-level understanding of the language. If you do, you're going to run into these data races for sure. And these data races and other memory bugs cause some of the worst security vulnerabilities in browsers. So if we wanted to take advantage of this fine-grained parallelism without the peril that these data races introduce, we couldn't just start hacking a parallel version of our code. We had to find a way to make it safe. So rather than starting a project to rewrite the browser, we started sponsoring a project to create a new language to write that browser in. This language is the Rust programming language. As part of its design, it makes sure that these kinds of data races don't happen. If you have code that would result in these kinds of data races, it won't compile. We started sponsoring work on Rust in 2009 or 2010. It wasn't until 2013 that we actually started putting it to use for a browser, though, to see whether or not it could create the kind of browser that we wanted. I don't know if you've ever heard of the term yak shaving, where you have to do one seemingly unrelated task before you get on to the work that you really meant to do. At Mozilla, we have some pretty big yaks to shave. But in 2013, once we had this language in hand that allowed us to code in parallel without fear, we started looking at how we could really introduce fine-grained parallelism to the browser engine. The project that we started to do this is called Servo. It started by looking at this rendering engine pipeline and asking, what if we parallelize all of the things? So this means that we're not just sending the different content windows with different pages to different cores. We're taking a single content window and splitting up the different parts of that page. This means if you have a site like Pinterest, each different pinned item can be processed separately from the others. So for example, you could take CSS and you could send each pinned item to get its CSS filled out by a different core. This means that you can speed up the different parts of the rendering pipeline by however many cores you have, which means that as chip manufacturers add more cores into the future, these pages are going to get faster and faster automatically. This is the key. This is why this fine-grained parallelism is so important and why we invested so much time and risked so much in pursuing it. Because it wasn't actually clear at the start of this project that this was going to work. Creating a language that would support this fine-grained parallelism and then actually implementing a browser that used that language was a tough research problem. But that time and effort has paid off. We found out that these ideas work and that they work really well. So over the past year, we started bringing part of this into Firefox. We did this as part of Project Quantum, which is a major speed up of Firefox that we've been working on for about the past year. So it's kind of like replacing the parts of a jet engine mid-flight. And the first release of Firefox Quantum came out in November. One thing that we brought over is our parallel style engine called Stylo. So that splits up all of the CSS processing across the different CPU cores, as I mentioned before. It uses a technique called work stealing to split up that work. So whenever a core runs out of work, it can steal work from the other cores. And this makes splitting work up efficient. It also makes it possible to speed up the CSS style computation by however many CPU cores you have. Another piece that we're currently bringing over is called WebRender. So WebRender takes the paint and composite stages and combines them together into a single rendering stage. It uses the hardware in a smart way to make painting the pixels faster, which means that it can keep up with those larger displays. To do this, it uses another highly parallelized part of the computer, which is specifically meant for graphics, the GPU, the graphics processing unit. The cores on the GPU are different from the cores on the CPU. So instead of having 2 or 4 or 6 of these cores, there are hundreds or thousands of them, but they can't do things independently. They have to all be working on the same thing at the same time. You need to do a lot of planning if you want to maximize the amount of work that they can do at the same time. And that's what WebRender does. With WebRender, we can get rid of performance cliffs that trip up web developers. For example, if you animate the background color right now, it can make animations on the web start and stop. It can make it look janky because Paint and Composite have too much work to do. Because of this, there are currently a lot of rules about what you should and shouldn't animate on web pages. We're going to be able to get rid of these rules, at least a lot of them, so web developers don't need to hack around these performance cliffs. We can take pages that render in Chrome at 15 frames per second today and bring them up to the maximum FPS, whether that's 60 or 120 frames per second. But it's not just the browser's own code that the browser is going to need to run faster. It's also going to need to run application code faster. What I'm talking about here is stuff like JavaScript. So the JavaScript engine is a part of the browser I haven't talked about yet. Let's see where that fits in. JavaScript gives you a way to change the document object model, that thing that we got from parsing. When you change it, it triggers the creation of a new version of the page through this rendering pipeline. A lot of sites these days are pretty JavaScript heavy. That's where they spend a lot of the time that they have, a lot of that 16 milliseconds that they have to figure out what the next version of the page should look like. These sites are using frameworks like React, which does a lot of calculations in JavaScript to figure out what needs to change in the DOM tree. Now, browsers can make the JavaScript engines that run this JavaScript faster, but JavaScript isn't really designed for machines to run it quickly. It's designed to be easy for humans to write. The way that JS engines get fast is by making guesses about your code and where it can take shortcuts to run your code faster. But sometimes those shortcuts don't actually work out well for your code. And there's only so many shortcuts that we can bake into the JavaScript engine, which means that there's only so much that the JS engines can do to speed up app code. But what if app code could run in parallel? What if it could take advantage of the multiple cores in the same way that the browser's own code is doing? Over the past few years, browsers have been adding features that make this possible. So one that you may have heard of is web workers, which have been in browsers for a few years. These allow you to have JavaScript code which runs on different cores. You may also have heard of shared array buffers, which started landing in browsers this past summer. Now, unfortunately, because of the Spectre bug that was just disclosed a few weeks ago, the shared array buffer had to be turned off. But we're hopeful that we're going to be able to turn them on again soon. What shared array buffers do is give you that shared memory that I was talking about before, which you need for speed a lot of the time when you're working with fine-grained parallelism. But like I talked about before, it's pretty tricky to actually manage that shared memory on your own, and web workers can be hard to use. That's why so few sites and applications use them today, even though they've been around for years. It would be nice to have a language like Rust, which give you those guarantees that you're not going to have data races and which make it easy to split up work across different cores, across the different web workers. Well, there's actually another standard that landed in browsers this past year which helps with this. WebAssembly makes it possible to run other languages besides just JavaScript in the browser. Now, it doesn't quite have access to the DOM yet, but the working group is working on direct DOM access. And they are very close to finishing the work on threading. Once shared array buffers turn on, it should be ready. And that will make it possible to work across the different cores. There are also other things about WebAssembly that help application performance. It was designed for machines to run it fast, not to be easy for humans to write, because developers usually don't write WebAssembly directly. Instead, they write a higher level language, something like C or C++ or Rust, and then compile it down to WebAssembly. So that means that WebAssembly doesn't have to be easily readable for programmers. And that means that the engine doesn't have to do that guesswork that it has to do with JavaScript. This speed of WebAssembly, even without threading, is what's making it possible to run PC games in the browsers today. So these standards, web workers and shared array buffer and WebAssembly, make it possible for applications to take advantage of parallelism too. For example, in a framework like React, you could write the core algorithm in parallel. And that way, React could figure out the changes between the previous version of your application and the next version of your application, and it could distribute that work across all of the cores. Another framework called Ember is already starting to experiment with WebAssembly in their new Glimmer VM. And so they may be able to take advantage of this as well. I think we're going to see a big shift towards using these standards in the frameworks of web applications today. So let's get back to this challenge that we had. Here are the pieces of the puzzle. Here's how we address this challenge. This is what browsers need to do to support the new devices and the new applications that are coming to the web. There's the coarse-grained parallelism of splitting the different content windows in Chrome among different processes. There's the fine-grained parallelism of splitting up the work that's done across a single web page across those different cores. And then there's enabling application code to be parallelized as well. The coarse-grained parallelism is already there in all of the browsers. Chrome was the first to do this, but pretty much all of the browsers have caught up at this point. Enabling application code to go parallel, that's something that's happening in standards bodies, and it's being adopted by all of the major browsers. It's this fine-grained parallelism that's still a question mark. This is where most browsers have done the least so far, and it's actually not clear how to do it in most browsers, because the C++ that most browsers are written in is actually pretty hard to parallelize in this way safely. But I think that all of the browsers are going to need to do it. We may be the first browser to get there. We may be the first to get this fine-grained parallelism in place and deliver these speedups, but we really want the other browsers to get there too and to get there with us. Because that's the way that we're going to keep the web going. That's how we're going to keep it healthy and vibrant no matter how much the browser's limits are pushed. Thank you all for having me, and thank you for listening. Okay, so we have a question.
So the shadow DOM is a new feature. Obviously, the frequency and order in which the DOM is updated dramatically affects user experience. The shadow DOM is one way to filter that, right? Are you guys looking into incorporating shadow DOM as an integral part of the browser so that any framework can use it without having to have all that JavaScript on the side?
The question is whether or not we're planning to incorporate the shadow DOM as an integral part of the browser. We are implementing shadow DOM right now. We don't have it, our implementation is still in progress, but we are also planning on using that web components because Firefox is actually built using HTML. We're moving away from our custom Zool and XBL and moving towards having the entire browser in HTML, JavaScript, CSS. So we're actually using web components for that, and Shadow DOM is part of that.
Right, so at that point, then they could just drop all the JavaScript that's safe, for example, React and these other guys use to manage their own Shadow DOM and let the browser kernels away.
So there's actually a difference between the virtual DOM, which React has, and the Shadow DOM. They actually address different problems. What the virtual DOM does is figure out the difference between a previous version and the next version. A shadow DOM gives you encapsulation of your DOM. React is probably not going to adopt a web component strategy for their what they do. But you can use frameworks that have web components.
So when will I be able to program in Rust instead of JavaScript?
Oh, okay. So that is a good question. You can kind of, sort of, a little bit do it today, but the support for it's very experimental. So you will run into bugs for sure. But that is actually one of the projects that I'm currently working on, is trying to improve the tool chain for that. And I mentioned Ember, this JavaScript framework. They're trying to convert. They basically have this, the way that they handle changes is not a virtual DOM, but it's an interpreter, a bytecode interpreter called the Glimmer VM. And they're hoping to have a WebAssembly version of that done within the next few months.
And will you have
with
an
Rust.
IDE with a debugger that works?
So we actually do, we don't actually need to build our own IDE to have that. We do have very preliminary support for source maps that allow you to go from WebAssembly back to Rust in the browser, in Firefox. So in the developer tools, we have that support. And we can then allow Visual Studio Code, all of those other IDs to leverage that. Yes?
How many cores are you planning to support for the near term? And how many do you think there will be diminishing returns as you get up to 32?
Well, the nice thing is the architecture that we have doesn't restrict. Like, however many cores you have, we can use them all. So the architecture will expand automatically. Oh, sorry.
Infinitely.
Yes.
Arise a persistence of vision.
Uh-huh.
So just going beyond 60 frames per second, does it bring in any new fidelity?
I don't actually know. I assume that it does because if you go less than 90 frames per second, you get motion sickness with VR experiences. So I assume you can perceive the difference at some level. You might not consciously perceive it, but your body is perceiving it. I don't know when you go past 90 frames per second, how much of a difference your body even feels.
Do you have benchmarking results between the parallelism that your browser delivers versus what Chrome delivers to their parallelism?
So there are a few different benchmarks that you can use but they measure, it's tricky to figure out what to measure. So there's speedometer, which is something that the WebKit team put together. I know that there's also some benchmarks that are specific to the CSS processing, but I don't know the numbers offhand.
A lot of work is going into allowing independent JavaScripts from different sources to run on the same page securely.
Mm-hmm.
What about these higher level languages through WebAssembly?
That's another good question. So we actually operate in the same sandbox as JavaScript. It's actually the same engine that runs WebAssembly and JavaScript. So we have a lot of the same security properties. One thing that WebAssembly does give you is, well, JavaScript also gives it to you, is you have this array buffer. It's basically just, you get direct access to bytes. And so people are really concerned that that could be a problem, if you have a malicious code that can dig around in bytes. Well, you're only allowed to look at the bytes that are in the memory that is assigned to your module. If you try and access something outside, it does an array bounds check and you'll trap. And the addresses, like your pointers, your function pointers aren't actually stored in there. You have to use the thing called call and direct. So you don't actually have the memory addresses in that, so that you can't have malicious code that changes those memory addresses.
So what about in your browser window, if you have, say, a second sort of mini application running picture-in-picture,
Mm-hmm.
can your engine still handle that? Maybe dividing it up between two sources, perhaps, or more?
So we can handle that with the current browser. There's also some work that's going on in Servo to make that even more parallelized and basically to isolate those more. I honestly haven't dug into those details too much, but the Servo project would have, if you looked there, you'd find more information about that.
Okay, well, thank you very much.
Thank you.
See you later.
Thank you all.